I am working through chapter summaries for the textbook, Matter and Interactions. I didn't even write that down, but M and I. And this is for the second semester, the calc-based second semester physics, Matter and Interactions, Chapter 16, let's go. And I just want to talk about really briefly so the biggest ideas that we need to move forward, because Chapter 16 has a lot of stuff in there. Number one is this. This is the electric field due to a point charge. So if we have a charge, it creates an electric field around it, and we can calculate that electric field. If you need to look back at the other summaries, do that, but we can find that. That's an important thing. We can find that as a vector value. If we have more than one charge, it's just the vector sum of those things. The other thing that we're going to use, it's just a result that we're going to use, is the idea that if I have two parallel plates that are equally and oppositely charged, the electric field inside of there is fairly constant if those plates are close together. And we can calculate the value of that. It doesn't even really matter what it is, but it's the charge over area over epsilon naught. Okay. So now let's take a second and jump back to the previous semester. The work energy principle. And this is technically a review, but maybe not. So in the first semester, you did a couple things. You did F net equals dp dt, where p is the momentum. This is the momentum principle. You can rewrite this as Newton's second law if it makes you happy, but it's the same thing. And then you did the work energy principle, and it looks like this. Work is the change in energy. And that looks silly, okay, but that's basically what it is. And then we had, the first thing is, what is energy? Well, energy of a particle is it's mc squared plus k. This is the mass of the particle, that's the speed of light squared, and that's the kinetic energy. And so this is the most generic version of that, and you can't write k very easily, but this is what it is, right? So a particle has energy because of its mass, and then this is because of its motion. And this can get pretty complicated, but it's super important. However, if this is very slow, then this term we could assume is fairly constant, and then k is approximately equal to 1/2 mv squared. So that's your kinetic energy. And if you just have a particle, that's all you have. Now, what about work? Well, if the field is constant, if the force is constant, so I'll put constant force, and I'll spell it wrong, constant force, then work, and the path is constant, F dot delta R, where F is the force, delta R is the displacement. So if I imagine I go from here to there, that's my vector point A to B, that's the vector delta R, that's the force F. Let's do a quick review of dot product. If I have two vectors, A, which is AX, has an X component, that's a Y component, a Z component, and B has a X component, a Y component, a Z component, B, I'm thinking ahead. Then the dot product A dot B would be simply the X components multiplied, AX times BX, plus the Y components multiplied, AY, BY, plus the Z components, AZ, BZ. So you get, the important thing here is when I take the dot product, I get a scalar value. Okay, so when I do F dot delta R, I get a scalar value, which is good because energy is also a scalar. And that's one of the things about energy, is it's a scalar thing. Now, there is another way you could do this. A dot B can also be written as the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between those two vectors. So that's work. Okay. Now, one of the things that you may or may not remember from your previous semester is things like this. Well, if I have path, and let me look at my thing right here. Let's say if I calculate the work and it's equal to, let's just say this, path independent. So suppose I go from A to B along this path, and I calculate the work. And then I go along this path, and I get the same work. That would mean the work along the closed path is 0. So if the work along a closed path, I'll write this as F dot dl, is equal to 0, then this is what's called a conservative force. Conservative force. And if the force, the work done by that force, does not depend on the path, then we can actually move that to the other side of the equation. So we have this work by some conservative force is the change in energy. So if I move that to the other side, I can write this as 0 equals delta E plus delta U, where delta U is the change in potential. And so that's going to be negative the work done by the force. So we define work, the change in potential, as negative the work done by that conservative force. Now that only works if the work done is path independent. And gravity was like that, so we ended up having a gravitational potential energy, U equals mgy. We had a better gravitational potential energy, U equals negative g m1 m2 over r. And we could look at the change in potential instead of the work done by those forces. So it was a really powerful way to do things. And we can do the same thing for the electric force and the electric potential energy. So let's look at an example. Suppose I have parallel plates. I told you we're going to use this. So this is positive. And this is negative. And I have a positive charge right there. Well, there's going to be a force pushing on that. So imagine that force, which I can calculate, F, is just Q times E, and E is constant. And now suppose that I let that particle move from here to there, a displacement delta R. Well, I could calculate the work done on that force, that particle. So the work is F dot delta R. That's not too hard, which would be QE dot delta R. But it turns out that that work does not depend on the path. So I could move that to the other side of the equation, and I get delta U equals negative QE dot delta R. And that's for that change in potential right there. And that's just the same thing as what we did for the previous semester. You did that with gravity, both constant gravity and real gravity. It's the same thing. So we call this delta U. We'd like to call this, this is the change in potential energy. Potential energy. Now here's something that gets a little weird. If I divide both sides by Q, I get delta U over Q equals negative E dot delta R. And I call this something the potential. And that's really weird. We don't do that in gravity. We don't have a potential. We just have potential energy. So this is actually a change in potential, and we call this delta V, and we have units of volts. So potential energy is in, change in potential energy is energy, and it's in units of joules. Change in potential is a change in potential energy per charge, and it's in volts. And it seems like it wouldn't be a good thing to do, but it turns out to be very useful. And you can see right here that if the field is constant, delta V is negative E dot delta R. And that's only for constant fields, okay? Now, I do want to point out one other thing. If I have, that we have this delta V in volts, there's this other thing called an electron volt. Where this is the energy for one electron going through 1 volt potential difference. So if I go over here, I can calculate that, right? If I know this is delta U, I can write this delta U is Q delta V. So if I know Q is 1.6 times 10 to the negative 19th coulombs, and delta V is 1 volt, I get 1 electron volt is 1.6 times 10 to the negative 19th joules. And that's just a unit conversion that we see, and it's a cool thing to write. So I just want you to be able to be cool, okay? Okay, so this is how, let me go back one other step right here, because suppose that I write my electric field. Let me put this on another piece of paper. So we're still in a constant field, and I have right here delta V is negative E dot delta R. So suppose I have this parallel plate, and the electric field's in the x direction, but I don't really care, and I'm moving in the x direction, so that's E, that's delta R. I can write E as the vector EX, EY, EZ. And then delta R, let's just say for now, yeah, let's write this as delta X, delta Y, delta Z. So the dot product over here is going to be negative EX delta X minus EY, that's a Y, delta Y, minus EZ delta Z, and that's going to be delta V. So if I just take one of these terms at a time, I can, let's just say it only moves in the x direction. If it only moves in the x direction, then negative EX delta X is delta V. So I can actually use this to calculate EX. Suppose I know the change in potential, I can use that to calculate EX. EX is negative delta V delta X. And that's only true for a constant field. And then I could have EY is, that's a Y, negative delta V delta Y, and then EZ is negative delta V delta Z. And if I let the limit of these, take the limit as delta X, delta Y, and delta Z go to 0, I actually get this. EX is negative the partial of V with respect to X. So the partial of V with respect to X is hold all the other variables constant and just see how does the electric field change in the x direction, and that can give me how does the potential change in the x direction, and that can give me EX. EY is going to be negative del the partial of V with respect to Y, and then EZ is negative the partial of V with respect to Z. And we can actually write this in a really cool thing using the del operator. It looks like this. We'll use this later. Del is the vector partial with respect to x in the x direction, partial with respect to y in the y direction, partial with respect to z in the z direction. In that case, E, the vector, is negative del vector v. And we're going to come back to that later. Okay, what about the electric field and the electric potential in a conductor? So imagine I have a conductor, and it's doesn't really matter if it's positive or negatively charged. Let's just say it's neutral, but there's an external electric field. Well, remember, we know that E equals 0 inside. And it has to be, otherwise those charges could move. Now imagine I want to go from here to here, from A to B. Well, if the electric field is 0, what do I know? I know delta V is also 0. But here's the important point. Delta V is 0 does not mean the potential is 0, right? Because this is always a change. If I come from over here to here, then I may get a value right there. These two have to be the same potential, but they don't have to be 0. Okay, that's an important point. Let's look at the potential due to a point charge, because it's something that's going to be very useful. Suppose I have a positive charge right there. And remember, delta V is negative E dot delta R if constant E. But here I do not have constant E. So if I look at this along the x direction, suppose I want to find the potential at the position R with respect to infinity, because it's always a change. I know the value of the electric field in the x direction. Let's call this a distance r. E, the x component, because we're only in the x direction, is 1 over 4 pi epsilon naught q, that's a q, over x squared. Right? That's my electric field due to a point charge in the x direction. Now suppose I want to go from here, infinity, to r. Well, the field is changing, so I really have an infinite sum of a bunch of tiny little steps. So let's do that as an integral. So delta v is going to be the integral from negative the integral from r equals infinity, or let's say x equals infinity, to x equals r. And then I have, this is my electric field, 1 over 4 pi epsilon naught q over x squared. And then my step size is going to be delta x. So if I integrate this is a constant right here. I have negative 1 over 4 pi epsilon naught q, and then the integral of 1 over x squared dx. Well, I can do that, right? It's just a power rule. So I'm going to add 1 to this and divide by that. So this is x to the negative 2. Add 1, I get x to the negative 1. Divide by negative, I get 1 over 4 pi epsilon naught q over x from infinity to r. So this is going to be 1 over 4 pi epsilon naught q over r minus 1 over 4 pi epsilon naught q over infinity, which goes to 0. So this is my potential with respect to infinity. Okay, and so you'll see this a lot. We'll say, oh, due to a point charge is 1 over 4 pi epsilon naught q over r, but that's the potential with respect to infinity. We always have to have a point that we measure the potential with respect to. In this case, we're going to say the potential at infinity is 0, so the potential at any other point would be this. We can use that to find the change of potential between any 2 points. Imagine that I do this. Suppose I have a point charge right there, and I want to go from here to there. So this is R1 to R2. Well, I could do the integral from R1 to R2. So I could say delta V is going to be the integral from 1 to 2 of negative E dot dl. Let's just call that dl. And I could do that. It's not that terrible of an integral. But I could also say that's going to be equal to V2 minus V1. So I can find the potential at 2 with respect to infinity and the potential at point 1 with respect to infinity. And that can be my change in potential. So it's a different way of thinking about the whole thing. Now, what if I do this? What if I do some complicated box like this? So I go from 1 to 2, and then I go back up here. I mean, we said that it's path independent, right? So if I go from here to there, that's the same as going the opposite of going from here to there. So it doesn't matter what path I take, but if I end up at the same point, the potential should be 0. And this is something we're going to see later. Delta V loop equals 0. And that's the loop rule when we get to electric circuits. And it's not always true. I'm just giving you a little spoiler alert here. This is delta V due to loop is 0 if we have electric fields made by charges. If you just want to make electric fields by charges, then that's true. Okay? There's another way to make electric fields. And I'll save that for later. Okay, what else do we have? I'm looking at my notes here. Oh, one of the other things they talk about, what if you have like an insulator and you apply electric field, E applied, and inside there's going to be these dipoles forming, and then if I want to calculate the change in potential across that, then how do I do that? Because you can't really integrate through the dipoles. But what happens is we get an effective field inside, and we call that E inside. It's going to be equal to the applied field, EA, divided by K, capital K, where K is called the dielectric constant. So it's one way to take into account what happens when you put insulators in an electric field. And now I just want to talk about one other thing, and I'm not going to go through the derivation, but what the basic idea is, suppose you have a capacitor like this. We know that it makes a constant electric field. And suppose I want to pull this plate out a little bit. Well, I'm going to have to apply a force to that, and it's going to move a distance. So if I apply a force, I can calculate the change in energy. I can calculate the change in potential energy due to the force. And then I can calculate the change in volume because it's going to get bigger, right? I have a constant electric field in there, and so it's going to be in a bigger area. And it turns out that we can get the change in energy per volume, per change in volume, and it is 1/1/2 epsilon naught magnitude electric field squared. And we call this the energy density for the electric field. It's not important now, but it's going to be important later. Okay, I do want to say one more thing. Suppose I have a ring. We did this before. So here's a ring of charge in the XY axis. So it has a radius R and a charge Q. And I want to find the electric potential on the Z axis like I did before. And so here's it looking from the side. And that's the charge Q. Okay, so I want to find the potential V right there. Well, we did this before with the electric field. If I want to find the potential there, the potential also obeys the superposition principle. And so that means that the V is going to be V1 plus V2 plus V3, so forth. So I can take all of these points on the ring and treat them as individual points to find the total potential right there. And it turns out that it's very easy in this case because V, the potential, is a scalar. So when I find all these values, it's really easy to add them up because I don't have to worry about how they add as vectors. It's just adding them up as scalars. And I'm not going to do the problem, but I just want to point out that if you have a charge distribution, you can do a similar integration where we find the potential due to these points, add them up as an integral, and get the potential. And it's possible then to find the electric field from that. But remember that the electric field, if I know the potential at this point, I do not know the electric field, right? The electric field depends on how the potential changes. So I actually have to move this back and forth that way, move this back and forth that way, and in the other directions too. And then by looking at how the potential changes in those directions, I could find the X, Y, and Z electric field values. And I probably will do that as a problem, but I just want to point that out. Superposition does work for electric potential, but it doesn't directly give you the electric field. You still have to do some work. So if you want the electric field, sometimes it's easier just to integrate over the electric field. Sometimes it's easier to integrate over the potential. Okay, there's a lot of stuff there. Like I said, we're only going to learn this stuff by doing problems. Read the book. The book's great. I'll post some more practice problems. The end.